recorded.
Okay, good morning. We were discussing component variations. That is, you expect the component parameters like resistivity, sheet resistance, or threshold voltage to have some values, but they will not have those exact values. There will be changes. So, like I said, there are process variations which are related to the foundry and when it is fabricated and so on. And every run there will be something. And then there are variations across temperature, and semiconductor properties are especially sensitive to this. Resistivity also could be sensitive, capacitance not so much, and so on. And then finally, there are supply voltage variations. That is, this is nothing to do with the foundry itself, but you expect that the supply voltage that you have for your IC will not have the exact value. And maybe because of the same reasons, because that supply is generated by another IC and it has its variations and so on. Okay. So you have to design an IC to take into account all of these. So these process variations, again, it entirely depends on the process, but typically resistance variations could be as high as plus minus 30%. The same goes for the current factor of the MOS transistor and so on. Okay, it could be even higher. Capacitance may be a little bit less, 15 or 20%, but you have to, these will be given in the process description and you have to use that. And temperature, basically all these will be strongly dependent, whereas capacitance and inductance will be probably only weakly dependent. Yes. No, temperature is on a single IC, right? I mean, as you heat up and cool the circuit, the properties will change. No. So it could be within also if the temperature of one part of the die is different from another part of the die. Okay. No. Now there is nothing to consider. This is something to be taken into account during design, which basically you need to know the range of values. But these are sort of, we for now take them as common to the IC. That is, all components vary in the same way. Okay. And the supply voltage you expect plus minus 5 to 10%. I mean, 10% is expected, and these are called PVT variations. Okay. Now there are many ways of dealing with this. There is no single recipe that works everywhere. One is you make the circuit insensitive to these variations. This is possible in some cases, like the amplifier we saw. You use negative feedback and you just make sure that the loop gain is high. The loop gain can vary, but the closed loop transfer function doesn't vary as much. The other one is, okay, you let it vary, but have a reconfigurable component that will be adjusted to have the right value. Okay. So there are many such things. And somehow locally you can make sure that the variations are small. Okay. So this is an example of a negative feedback amplifier, and you can also reconfigure components to combat variations. Okay. Now, so far our assumption is that components are matched on an IC. That is, if I make two identical resistors, I may or may not know whether they're 1 kilo ohm or 1.1 kilo ohm, but both will have the same value. That's the idea. Now, even that, it turns out you have to be careful. One, there can be systematic variations depending on how you make them. I will illustrate them with resistors, but the same will hold for everything. Okay. So let's say I make a resistor of length L and width W. Okay. And I have a contact over there and a contact there. Right. And let's say I want to make an amplifier of gain 2 or minus 2. So R and 2R. So I'll need two resistors, right? One of value R, another of value 2R. Okay. So now I'll make another resistor which has length 2L and the same width W. Okay. And of course, this is supposed to be R and this is 2R. Okay. So if I do this, do you expect the gain to be, the resistor ratio to be exactly 2 or could it be different from 2? Why? Why? Fields. What fields? Okay. No, it's not okay. Metal or you have multiple metal layers and you can make connections between them by essentially poking holes and filling them with metal. Okay. So you have on an IC, if you want to make connections between different layers, this may be polysilicon resistor, and to connect to this, you will have some plug and then another metal layer. Okay. So now one of the points is that what is the resistance of this? What is the expression for the resistance? R. It's the sheet resistance times L by W. Okay. This is sheet resistance times 2L by W. That's why we think this has twice the resistance as that one. But where does this formula come from? I mean, this basically came from rho times A by L, but what is the assumption here? Sorry, rho times L by A. Why is the resistance inversely proportional to the area? Okay. That assumes that the current is uniformly distributed across the cross-sectional area. That is not true because in the end you make some contacts and the current will be crowded towards the contacts. Okay. So there are ways of modeling this accurately. We won't get into that. I mean, the ends will behave differently from the middle. Okay. But the point is, I want to make a resistance, I want to make an amplifier of gain 2. I want a resistance ratio of 2. And I know that now there are these uncertainties. Okay. Because somewhere in some region towards the end, okay, this formula doesn't hold. So how do I make sure that I get a resistance ratio of 2? I don't want to have to worry about the detailed modeling of this three-dimensional spatial modeling and so on. So what should I do to make sure that I get a resistance ratio of 2? The only way, this is the standard technique in IC design, is you make three copies of this, and then for R you use one of them, and for 2R you use two of them in series. Okay. So as long as they are identical, I mean, maybe they have some proportion of this end resistance which you cannot predict with a simple formula, and in the middle the current density is uniform. The point is all three are identical to each other. Okay. So this means that you will get 2R and R. So this is a very standard thing to do in IC design. You try to make everything some multiple of a unit component. Of course, this doesn't work very well when you have non-integer ratios. You can try to approximate it with rational numbers. Even then, I mean, it may be a problem. I mean, rational numbers are P by Q, but if both P and Q are very large, you will have to make a large number of each of them. Then you have to resort to some approximations and tolerate more errors. But when you want precision, this is the way to do it. Okay. So you make everything unit element based. Okay. So, and this is true for everything. If you want a current mirror with a ratio of 2:1, this is what you will have to do. I'll show the physical layouts. If you want a capacitance ratio of 2:1, it's the same thing. Okay. So this way, there will be some contribution from the edges which you can't predict with simple formulas. All those will be taken care of, right? Any questions? There is also another practical reason to do this, that is to adjust the aspect ratio to be manageable. I'll come to that when I come to MOS transistors, but it applies to every component. Okay. So this avoids the systematic mismatch. By systematic mismatch, we know that there is a mismatch, but it may be difficult to calculate because this, in this case, on the left side, we know that at the end something else is happening. But to sit and calculate that resistance is also not easy. Okay, they'll be predicted in the model, but anyway, you can simply avoid the problem by using this. Okay. Any questions? And of course, this there will be some directional sensitivity. So if you want two identical resistance, in principle, these two may be the same. That is, this is W and that is L, whereas this is L and that's W. We have used the same layout, but because they are in physically different orientations, they won't also match well. By the way, one thing I didn't mention in IC design, again, these things will become more relevant when you do layout. Basically, everything is laid out in two directions. Okay. This is called Manhattan geometry because of the way streets are in the city of Manhattan. So you have only horizontal and vertical lines. You can have 45-degree lines in some cases, but everything is laid out like this. Okay. So this you don't do. If you want two identical resistors, you orient them in the same way. Okay. This is how you do things to avoid systematic mismatch. Right. Now it turns out again, even these can have errors. Let's say I make these three identical pieces and with the same goal, I want resistors in the ratio 1:2. Many times what happens is there is some sort of gradient across the chip. Okay. That is, the doping level could vary as you go from, let's say, left to right. Okay. It can be in any direction. We can generally assume that to be linearly varying. So what will happen in that case? If this piece has a value R, this will have some slightly different value, and this will have something that's even more different. Okay. So there is a linear gradient, and this can happen because of the process itself. Somehow the process has some bias, and then there's some doping slightly increases from one side to the other. It can also happen because of temperature. That is, like I said, it's not true that all parts of the die will be exactly at the same temperature, all parts of the IC. You could have some transistor, let's say on the left side, which is dissipating a lot of power. So that is itself heating the chip. If you have a heater here, so obviously its effect will reduce as you go further down. So the temperatures could be different here, there, and there. Okay. And we can assume that dominantly it is a linear behavior. That is, the increment, we'll assume, of course, that they're equal spacing. So you have R plus delta R plus 2 delta R, and so on. So clearly in this case, the ratio is not 1:2. So is there any way to now fix this? Yeah, exactly. So this is not how you should configure it. We should have the center one must be the single element, and the other two you connect in series. Okay. So this will be R, and so the middle one will be R plus delta R, and the others will be 2R plus 2 delta R. Okay. So this is again another principle that is used with linear gradients. But what is the general idea here? What should we do when we have, let's say, multiple units and so on? We want a component. Here we had only 3 elements. So we put the single element in the center and the others in the on the sides. But if you have a general case where you have a lot more units, what is the idea? No, it doesn't matter actually. As long as, so this is actually the key thing that makes it work is it is linear. Okay. So what is this? What is the property between two elements that have to be matched with linear gradients? I think you know what this is. It's called common centroid. So if you have the same centroid for the two elements, then any linear gradient will cancel out by the definition of the centroid, right? You know what centroid is, right? Okay, if not, go look it up. But this is called so for instance, if you wanted elements 1, 2, and 4 in ratio 1 to 4, what would you have to do? What do you have to do? I mean, the principle is exactly the same. All three must have the same centroid. So you should, and 2 must be there. Their centroid will be over there. And okay. So all of them have the same centroid. They will have, as long as the gradient is linear, they will be in this ratio. Okay. So this is common centroid. This improves this type of, I mean, this combats this gradients and so on and improves it, but it also does complicate the connections because you may have to connect something here to something over there. Okay. So always you use the simplest technique that works, right? That's actually one of the most important principles of design. I mean, just because you know some complicated technique, it doesn't mean you should go and use that. Okay. So simplicity is one of the most important characteristics of design. So you have to use techniques that are that work. Okay. And if you use the simplest thing that works, that's probably going to be the most reliable design. Okay. So you use common centroid if necessary. Now there are other things that can matter. I mean, that will matter actually, and this is also very common, routinely used. So even if you make this the central one R and the other two 2R, There'll still be difference between these three because this has two neighbors, one on each side. And actually, these are all like very close to each other. So it turns out that these things matter. Okay. So without these two will be different from that one. Okay. So what is the solution to that? So you have extra devices, one or more. These are called dummy devices. This is just to make sure that the physical environment is the same for all elements. And you can have one or more. I mean, more may be required in some cases. Basically, you have to waste some area so that all the elements in the center are identical to each other. Again, this is not, I'm showing examples of resistors, but this is true for any element. Okay. So you have to add dummy devices to create identical environment. This again, this thing about systematic mismatch, there is not much to calculate or anything, but these are things that you need to know. That is, when you start doing design, that's when it makes sense. For now, it is just, these are just facts that you have to take. Okay. Because in principle, I mean, when you're drawing circuits, you can draw it any which way you want. Okay. But when you're physically making it, you need to observe symmetry, maybe common centroid, add dummy devices, etc., to minimize this systematic mismatch. Systematic mismatch, basically it comes from things that are known but are usually difficult to calculate and predict. It could be, let's say, a fringing field of a capacitor, which is proportional to the perimeter, whereas the parallel plate capacitance that you calculate is proportional to the area. Okay. So again, if you have capacitors of different shapes, that is, in principle, if you have this and if you have twice the width, they should have twice the capacitance of that. Okay. But very clearly, the perimeter of this is not 2 times that one, right? Okay. So you should use this unit element based design, or if for some reason you can't do that, the very least you should try to keep the perimeter to area ratio the same. Okay. So these are all things that you will have to do. By the way, the components can vary very widely in value, right? Like for instance, you have heard of digital to analog and analog to digital converters in some basic form, right? So in many such circuits, what happens is that if you have a 10-bit digital to analog converter, there will be some element. It could be capacitor, resistor, MOS transistor, some element which has a weight of 2 to the 9, and then some element which has a weight of 1. Okay. So that you can count from 0 to 2 to the 10 minus 1, right? So that's a very big 1:500, but that's actually not even the most complicated digital to analog converter you see. You can have 12 bits, and this actually increases exponentially with the number of bits, right? So you can have components with very different values, okay, where ratios which are very large, and you have to be able to make them precisely, and all these things become very important. Okay. No, that the gradient, that dummy device will not do anything to the gradient. If you want to combat linear gradient, you have to do some common centroid. I mean, if they're the same components, they will create the same environment, right? That's the idea. And I mean, when I say environment, everything should be the same. The spacing, all of that should be exactly the same. It should be like more identical devices placed but not used. Okay. Hmm? No, it does, right? I mean, even with the asymmetrical environment, the effect of temperature also could be different. I mean, they're all different, difficult to predict. Okay. But gradient is different. Gradient is they have different temperatures and you want to have identical values, then you have to use common centroid. Okay. Now, this, so basically, this is for all elements. You have to use unit element based, and this is also sometimes called ratiometric design. Okay. So that means they should also have identical orientation as well. Okay. And you may have to add dummy devices. And finally, you may need to use common centroid. Okay. Now, the reason I also said common centroid, you have to connect something here with something there, and it can make something complicated. You have to keep in mind that anytime you have a crossover of connections, that is, again, it's easy to draw wires like this when I'm drawing the circuit. Whenever you have something like this, you will always have asymmetry, okay? Because you will make connections on different metal layers. So if you have to go from, if you have to have two wires crossing, they'll be either in different metals, or even if they are in the same metal, this crossing part has to be in a different metal. They can't be in the same metal. So there'll definitely be asymmetry. So the more crossings you have, the more you will have of connections having to travel through different metals and so on, and you can't make them exactly symmetric. Okay. Now, just a little bit about MOS transistor layout. The principles I mentioned apply to every case. I'll not show common centroid layouts, but I'll show just the ratiometric layout. So let's say you have a current mirror. Okay. So I want a current ratio of 4:1. Okay. So how should I choose the width and length of these devices? What should I do? So if you just go by the square law model, what it says is simply that okay. Now, of course, if you do this with arbitrary values of W's, it just doesn't work, right? So first of all, this is uh, yeah. So this is basically this is not even true, right? We saw that actually when it go to velocity saturation and so on, this is not even true. Okay. So if you want some transistors to be matched, they have to use the same length. Okay. On top of it, you can't do this either. That is, you can't make for the same reasons that I outlined with the resistor, the ends will behave differently from the middle and so on. Not to mention, the layout becomes very unwieldy. Okay. So in a MOS transistor, you can have width that is very large. Okay. The length will be from a few nanometers. Okay. By the way, I did not mention this explicitly. So you have heard of terms like, I mean, for processes, something like, let's say, 65 nanometer process or 16 nanometer process and so on, or maybe 5 nanometer process now. Okay. What is all this stuff? Yeah, what parameter is it? It's basically some minimum dimension that can be fabricated in that process. Usually it used to be the minimum gate length. Okay. It is either the minimum gate length or related to how closely two metals can be placed to each other, the metal pitch. Okay. So it is in a way a measure of how small you can make your dimensions on the IC. So the minimum side will be restricted. The minimum gate length will be restricted to something. In a 65 nanometer process, it is 60 nanometers or something like that. But for width, there is no such restriction. Okay, that is, it depends on the amount of current you want to have. You can have widths of millimeters, tens of millimeters also. Okay, it only depends on the current. If you want a lot of current, amperes of current, you need to have very large values of W. Okay, and you can't really make it like this. You can't make a transistor whose W is like that and L is that way. Okay, it's just completely unwieldy. You certainly can't have 1 millimeter this way and then 100 nanometer that way. Right? So how do you make that? What do you have to do? So basically, you know that if you have parallel connections of MOS transistors, it's like adding up their widths, right? So and anyway, we also know that we need to make unit element based design. Okay. So essentially, this could be, let's say, M1 could be could have that W by L, and M2 will have 4 times. It's not a single MOS transistor of width 4 microns, but there will be 4 MOS transistors of 1 micron width. Okay. And the way they are laid out is also, you know that. So let me again show the cross section and the top view. This is a single MOS transistor, and from the top it will look like this. If you want to make a MOS current mirror, you need another transistor. Okay. The way you make it is you make these junctions common. Anyway, the current mirror has one of the terminals common, right? The source is common to the 2 transistors. Okay. So what you do is you just extend this and you have the second gate here and the third gate over there. Totally we have 5, right? So you just have these gate fingers like this. Okay. I won't use common centroid, but let's say this is this gate belongs to M1 and these 4 belong to M2. And you connect all of them together. Now, of course, when you have transistors like this, obviously this terminal here, that is common to M1 and M2. Okay. So this one here has to be that one. Okay. So now if you look at this, if I call this the source, drain 1 and drain 2. So this is the source, this is drain 1. So this is drain 2. So this is also the source and this is the source. So you have to connect these. This will be the source and this will be the output terminal, and this will be the input terminal, okay, of the current mirror. And you have to connect this D1 to the gate. Okay, maybe looks slightly confusing initially, but you get the idea. You just lay out all, like a chain of transistors, and each one is called a finger, and you connect fingers any which way you want. And this you do, and even if you did not have, and again the same things that I mentioned earlier will apply. The fingers at the end will behave differently from the ones in the middle. So you can add dummy fingers which are not connected to anything, okay? Or you make sure that they have 0 VGS. In that case, they will not be carrying any current, okay? So for instance, I can have extra transistors on the side, okay, which are connected to this, but I tie the gate to ground so that they don't carry any current, okay? So you have dummy devices. Basically, the dummy devices should be there to match the physical environment, but they should not electrically affect your circuit. That's the idea, okay? And you can have any number of these. By the way, if you have a case where you want identical transistors, but they do not have a common terminal, you can still make that in the middle somewhere. You can insert a dummy device, okay, so that this transistor doesn't get connected to that transistor. So let me maybe show this here. So let's say so these two can be one transistor, and these two can be another transistor. Now you can see they don't have any common terminals, right? Only thing is you have to make sure that this dummy transistor here, its gate is connected to ground so that it doesn't carry any current. That's all. So you can do this. I mean, again, once these things will start, these ideas will start making sense when you may do the layout, but you need to know these things, okay? And if you are simulating circuits in a realistic process design kit, you will find a difference between, let's say, having a 4 micron wide transistor or 4 identical 1 micron wide transistor. The currents will actually be different, okay? Is this okay? So these are all about systematic mismatch, and again, even with MOS transistors, you can use everything that I described earlier. Dummy devices I already showed. You can also have common centroid. That is, in this case, to avoid gradients, this branch could be in the middle, and this one could be on the sides. Okay, so that is very much possible, and you will have to do that. Is this okay? And this finger layout, it turns out also reduces the parasitic diodes, okay, because you can see that each of these drain areas or source areas is shared by 2 fingers. If you calculate the area of the source and drain parasitics, if you have a layout like this, where you have a single long device, you can just estimate that the drain and source diodes will be about half the size in this case compared to that one, okay, because they are being shared by 2 devices each. That calculation you can do yourselves, okay, you understand? So that is, if I had let's say 100 micron wide device versus 100 times 1 micron wide, which are laid out as in the fingered structure like that, you will have half the source and drain area, okay? Any questions? So systematic mismatch is there because, I mean, the properties of the component depend on the physical environment and so on. And also you have simple formulas for some parameters like the resistance, etc., which do not actually hold. There will be other extra terms. So to combat that, basically you have to use identical components, right? Unit element based design, okay? So this is something that you will need to know, and then those of you who will go on to do IC design will be practicing this, right? And you can make out the difference very easily in any realistic design kit. You will you can make a single resistor that is 10 micron long versus 10 resistors in series with each one being 1 micron, there will be a big difference. Okay. Any questions? By the way, when you are doing design, always design and layout, it always helps to plan it out on paper. And then when you do that, you can't make those elaborate drawings of MOS transistors. You can make stick figures to see. I mean, let's say you want to explore different types of connections. These correspond to the gates. And maybe you have a different transistor. You can try out different things. Okay. Actually, one more aspect I forgot to mention, one more source of systematic mismatch. Now, it turns out that during processing, I think you may have heard of these terms like ion implantation and so on. So essentially, you fire ions into the silicon wafer. Okay. And that is not done vertically, but there is a slight angle, some 7 degrees or something like that. Okay. Now, because of that, what happens is that although in principle, the MOS transistor is symmetrical, okay, that is, you can't tell the drain and source apart. So let's say you have one transistor where left side is the drain and the right side is the source, and another one where the length, everything is the same, but this is the drain and that is the source. In this, current will be flowing that way. In this one, current will be flowing that way, right? It turns out these two will have slightly different characteristics because of the way they are formed. Okay, these regions are formed with ion implantation, and like I said, that ion implants are not fired vertically, but with some angle. You can look this up. Anyway, as far as we are concerned, we don't have to worry about where that comes from. Only thing is these two are different from each other. Okay. So what is it that I need to do to, again, I don't want to worry about how much it is and so on, right? That is impossible. But as a designer, I just don't want to have to think about this. So if I want to make a current mirror, what was happening earlier in this fingered structure? So the current flows from drain to source in both transistors, right? So the current would be flowing this way in this, here, there, there, there. Okay. So M1 has current flowing from left to right, whereas M2 has 2 fingers with left to right, 2 fingers with right to left. So you can expect some mismatch also. Okay. To match exactly to M1, you should have had 4 fingers all with currents from left to right. So how is it that, what can I do to fix this? Along similar lines to earlier, right? Where for resistors, we didn't worry about what, we didn't sit and calculate what the edge resistance is and so on, right? We just said that if you make it in this way, if you make it unit element based, you will get 2 to 1 ratio. What is it that I can do here so that I don't have to worry about this asymmetry? Mirror. Okay. So what's the general idea? How should you make every MOSFET? Even number of fingers. If you make every MOSFET with an even number of fingers, there'll always be one finger, I mean half the fingers with current in this direction and other half in that direction. So even if they are slightly different from each other, as long as you have even numbers, you'll be fine. Okay. So this is another thing that is done in analog design. This may not be so important for digital design where that precision matching is unimportant. So every MOS transistor should have even number of fingers for matched characteristics. Okay. So this will take care of any other directional asymmetry that may be there. Any questions? Now let's say you do all the systematic mismatch, which essentially amounts to, you can even say, carelessness. That is, you didn't make everything identical, that's why it was there, but now you know how to do it. You make everything unit element based. Everything should be fine. But even then, it turns out that if you make, let's say, 1,000 identical, I'll use resistor example, but the same holds for everything. Let's say you make 1,000 identical units like this on a chip or any number. Everything is the same. The direction is the same. The width and length exactly are the same. You have identical environments, etc. They will still have different resistance values. Okay. Now, at this point, you have come down to something that you can't control at all. That is, for instance, basically, the resistance of any material is related to the number of free carriers available there, which is related to doping. The number of dopants per unit volume is not exactly identical, right? Because of this discretization, there will be some statistical variation in that. And this width and length, I am drawing these as absolute straight lines, but there also there will be some jaggedness. Okay, so this won't be look like this, but I mean, I'm showing some exaggerated picture, but a rectangle will really look like that. Okay, and these are random variations. Okay, these are not because of something that you overlooked or some systematic gradient or something. And then rho itself will be different because the number of ions implanted in this may be different from that one, etc. So if you do make a large number of resistors on an IC, and then look at the distribution of their values, you will see something like this. So let's say nominally they had to have a value R naught. You will find that the values will be centered at R naught, but you will have some typically Gaussian distribution that you see for anything in large numbers. Okay, there will be some R naught, and it will have some. This is going to be a Gaussian or normal distribution. The mean value will be R naught, and it will have some standard deviation. And this is true for every component parameter, and this is known as random mismatch. Okay. So this is something you can't avoid, and in fact, you can guess that the smaller the component you try to make, the more out of control it will be, and the more of this random variations that you will get. We'll see. We'll quantify that also. So you will have this random mismatch, and you have to first be able to calculate the effect of this random mismatch, and secondly, see what is it that you can do to either reduce the random mismatch or maybe use some circuit techniques to mitigate the effect of it. Okay, you either have to reduce the amount of random mismatch or you have to reduce the effect of random mismatch on the circuit. Okay, both are possible and used in different contexts, right? So now how do you, and of course you are not unfamiliar with random quantities like coin toss and die throwing, all these things, you know, and all of you I think have gone through probability courses as well. So how do you characterize these random quantities? What is it that you do? Obviously with the random quantities you can't say exactly what the specific outcome is, right? You can't say that this particular resistor will be of this value, but you can say something. It's not that you don't know anything either. So what is it that you normally specify? Yeah, some statistical measures, mean and variance are the common ones. So the mean here will be the nominal value that you want to design, and you want to know what the variance is. Okay. For instance, it may be for various reasons. It may be to just specify uh, Okay. This gain magnitude will be R2 by R1, but each one will be, let's say, R2 naught plus delta R2 by R1 0 plus delta R1. Okay. And if you, of course, we'll assume that this delta R's are much smaller than the mean value. Okay. The random effect will be small. Okay. We'll later see that we can use small signal analysis to calculate all of this. And this can be reduced to with this approximation. Okay. So this will be the gain of this amplifier, and this also is the nominal gain plus some delta, and this delta corresponds to these terms, right? In fact, I can even write this as A naught times 1 plus delta A by A naught. Okay. So this corresponds to those. So knowing the variance of these, I can get the variance of that. And then I can decide whether that is small enough. Okay. That is, I want to get a gain of 4. Now, if it varies between, let's say, 4.01 and 3.99, I may not care. But if it varies between 4.4 and 3.6, I may. Okay. So first I have to be able to calculate how much the variation is and then decide what to do with it. We'll go from there. Okay. Any questions? What is that? No, that is, yeah, roughly. I mean, for large transistors, it is like that because this width of this drain region will be the same, or length of this drain region. Okay. So now this part is shared by 2 of these fingers, right? Whereas in the other case, basically you have this, maybe I'll show it in the same direction. I have this on each side. So if you calculate it, you will see that basically because of that, drain area being shared by 2 adjacent fingers, it will become approximately half. Okay. Anything else? Okay then, see you all.